third semester, and we will have another round of seminars in the spring with that scheduled to be announced. But today I'm happy to be introducing Dr. Riley, and Dr. Riley is going to in turn introduce a couple graduate students that work in his lab, and they're all going to be speaking with you today. I think many of you know that Dr. Riley is an associate professor here. He's director of the graduate programs in the Department of Kinesiology. He has a bachelor's and master's degree from Ball State, and then also has a Ph.D. from the University of Colorado at Boulder. His primary interests are in neuroscience area, and that's what they're going to be talking with you primarily about today. And some of you also know that he's probably just as famous as his academic endeavors with his throwing career, where he's currently in Highland Games, and some of you may or may not know that he was an All-American hammer thrower at Ball State, and he's in the Ball State Athletic Hall of Fame. So you may not know that side of him, but he's accomplished in many ways. So with that, I'd just like to turn it over to Dr. Riley, and then he will do the other introductions from there. So thanks again for coming today.
All right, nothing like speaking into a microphone that doesn't work and being directed where to stand in front of the lights and not move. This doesn't really fit my style very well, because I don't know if you've ever had me in class, I don't sit still very long. But we're here anyway, so we're going to get through it. Go ahead and Davin, stand up first. So start with age before beauty here, but Davin Greenwell is a third-year Ph.D. student with me, and he did his undergrad and master's degrees here. Very accomplished so far in the work he's done. He's a great asset to the lab, and he'll be discussing some of the work he's doing pre-dissertation. So this is some stuff that he's been involved with since he started in the lab. So then Michaela Wilson. Michaela has also been here since undergrad. I've had the pleasure, absolute pleasure, of teaching both these students for a long time, and now advising, directing, fielding their breakdowns, everything. So this is what we do. But Michaela's in her fourth year. She is officially a candidate because she has passed her qualifying exam. She is on to the dissertation portion of her PhD. So very exciting. Glad to have both of them here. I really wanted to do this more to highlight the great work they're doing and to kind of give a little shine on what they're doing, because they carry the lab. I know there's a lot of professors in here right now. The professors will say, it's their lab. We all like to say Riley's lab or, et cetera. It's a team effort. We do a part, they do a part, and hopefully the end part is it's all successful. So I want to make sure I give recognition to them, because I won't do it to their face outside of here. So they got to soak it up while they got it. All right, moving on. How many of you are here for as part of a class? Raise your hand. Part of a class. You're here because of a class, because of a teacher. I won't use, there you go, good. Hey, whatever means get you here. Hey, as long as you're here, you're getting exposed to stuff. That's the most important part. If you're like me in undergrad, I had no idea research even existed. So while these things seem really funny, like I just got to go sit through this talk, some of you are getting exposed to stuff that might be a future career that you want to go down. So it's worth it. There's always those kids that came into college immediately knowing they wanted to do, biomedical research. And then there's the kids like me who was graduating undergrad going, what do I do next? So glad you guys are getting exposed to this. All right, on to the important part of today. In our lab, see, the selfish part of me, all right. In our lab, we do brain stimulation. So we'll talk more about exactly what we do with brain stimulation, but we do brain stimulation in an effort to increase or speed up the learning process. So not necessarily just, oh, I'm studying for a test, trying to speed it up that way, but how you learn to do basic tasks. So motor task, you're playing pool, you're shooting hoops, you're doing things like that. We use brain stimulation to try to accelerate learning of those tasks. So the topic for the presentation, brain stimulation, the newest PED, and it's the only pun you're going to get today because it's not performance enhancing drugs, it's performance enhancing device. It's usually the response I get. All right. So moving on, the general flow of the talk. We're going to talk about what is motor learning in general. All right. Talk about TDCS, so the specific brain stimulation that we use in my lab most commonly. The overall purpose of a lot of our studies. Then we're going to give you 2 published studies that my co-authors here were part of, and they're going to present those. All right, so recently published, as you can see, last year and this year. And then I'm going to have them talk a little bit about what they're doing currently and what they want to do for the future. So we're always, if you guys don't know the research process, once it's finally published, you've already moved on from it. So that's kind of where we're at. We're already looking ahead to all the stuff they're currently doing, and then in both their cases, even beyond that. All right, so what is motor learning? Very simply, motor learning is improvement of motor skills through practice, right? Anything you do, if you want to get better at it, you have to practice. There's no way around that. There's no cheat code. There's no, magic drug you can take where all of a sudden you're the greatest three-point shooter in the world. No, you get there by, how many of you guys have heard the 10,000 hour or 10,000 rep rule? Right? So it's a very common thing where people say that you need 10,000 hours of practice to become proficient at something, right? Well, in general, a little foreshadowing, we take the approach of what if we could knock that down to 5,000 hours, right? So the idea being, what if we could just speed up the time it takes you to learn anything? And I'm very interested in that overall. Wow, you can't see that at all. That's cool. All right, well, I'm going to talk you through it because we're here. Why not? Well, I can't move from my spot, so I've got hamstrung.
It's unique.
Okay. So there's a lot of different brain circuits up above here, but right here is the key one that we focus on, and that is the primary motor cortex. All right, so if you've had me for Mr. Fallowfield's 212, we talked about several different areas of the brain. If you've had me in my 452, we certainly talk about different areas of the brain. But the main area that we focus on, at least right now, the real walking stages here of the studies we're running, are the primary motor cortex, and it's highlighted up here. So it is a strip on basically the surface of the brain, right about here, that contains where all movement comes from. Now, there's a lot of other brain regions where the decisions for movement, where the shaping of the movement come from, so the cerebellum, other regions of the brain. But ultimately, all movement comes from this one region of the brain. There's no way of getting around it. It's where it comes from, right? So we focus a lot on that region. Now, when we talk about how we learn, we really go through stages. And you guys can apply this to anything you've ever done, right? Whether it be a musical instrument, a sport. You can't really think back to when you started walking. That's a little your recognition of it, but you went through it even then. So we go through these stages. We go through acquisition, so the initial acquiring of the skill. Consolidation, which is what we talk about as actually learning the skill. So we have acquiring, that's okay, I kind of get the idea of what I'm doing here. Consolidation is, I know how to do this. All right? Then finally, retention. So how long do you retain the skill? So not only do you learn it, but then do you know how to do it years and years later? The better way of putting this, if you want the layman's terms, is we have fast learning, we have slow learning, and then we have, do I even remember doing this? Right? So you guys can all imagine, how many of you grew up riding a bicycle? A lot of people, right? I would assume a lot of you, since you've been in college, unless you use the bicycle as a means of transportation, a lot of you have probably not ridden a bicycle for a while, have you? So there's always the old saying, right? Just like riding a bike. So any one of you could get back on that bicycle tomorrow or next week when you go home, right? You could get back on the bicycle, and within, maybe it's a little rocky start, but relatively quickly, you'll be able to start riding and look fairly proficient doing it, not, like a baby giraffe trying to control, right? So you'll understand how to do it. So these are the processes through which we learn, specifically with motor skill learning. Now, here's the thing, though. The adaptations that we're interested in differ with each process. So the first one is fast motor learning. So this is, I bring you into the lab, I have you try something new. I have you try a brand new video game. Brand new, never even hit the market, probably because it's not that fun because it's for research, right? I have you try a brand new video game. You're going to learn to play that video game better from the start of the testing session to the end of the testing session, correct? Hopefully, if you're paying attention, right? So the reason for this is, in general, you have more activation of that thin strip of the brain right here. Really simple. More activation, better playing the game. Now, how that happens in the short term is we've probably unmasked or disinhibited connections. What does that mean? Big fancy words. Unmasked, disinhibition, that's really a big word, right? Basically, you have these pathways there. You have roads already in place that were just blocked off temporarily. So what you've done is you've opened up those roads for business now, right? And we can use them. We also increase input to that region of the brain through or from other brain regions. So specifically the striatum, which is deep in the brain, and also the cerebellum, which is the little brain that hangs off the back of the big brain. If you've ever seen brain pictures, right? There's no better explanation, it's the little brain. But the key here with the fast motor learning is we're not really changing anything. This is very short term, we get better at something. But then we have slow motor learning. So this is more than one session, more than one day. This is, I bring you into the lab. Michaela's currently running a study that they come in for how many sessions?
4 sessions.
4 sessions. She loves it. So much fun testing subjects repeatedly, right? But I bring you in 4 sessions. You practice the task 4 times. Eventually, you're going to get better at it. Right? It is that way with anything that you do. You're going to get better at it. The difference with slow motor learning is now it's not just using the brain regions, getting them more active in general, but we actually get new connections through things called LTP, LTD, long-term potentiation, long-term depression. We're not going to go into what all those are because you don't really need to know right now. And then also with brain-derived neurotrophic factors, BDNF, we grow new connections. That's it. Really kind of simple idea. Reorganization, or we increase the map size. This is what this picture is looking at here on the bottom. So this is actually showing a brain region. The yellow activity is really echoey down here. This is kind of cool. All right, so the yellow activity here is like moderate brain activity. The red would be a lot of brain activity. The more you practice something over time, the more activity you get, an expansion of the activity regions in the brain. Right? So the more you use it, the more the brain takes over. Let me give you a really simple example, a study that I use for all my graduate classes. Think about individuals that are blind that read Braille. How do you read Braille? What do you use? Do you use your elbow? Do you walk up to the door and like, How do you read Braille, guys? Not a difficult.
With your hands.
With your fingers, right? Fingertips. So what happens in individuals who are blind that read Braille is the region of the motor cortex devoted to the fingertips expands. Because think about it. Now, that's taken over a lot of their other processes in terms of how they communicate, right? So those brain regions expand. When you do any type of learning task, this expansion happens the same way. Now, is it quite as much as, an individual who's blind reading Braille? No, but it expands quite a bit. Another really good example, if I brought any one of you into my lab, if we did imaging right now, the region of the brain for your thumbs would be much larger than it was 20 years ago. Why? You use your thumbs more. Brilliant. Why do you use your thumbs more? Phones. Right? You guys spend, and I know you get the alert every Sunday morning or whatever it is, your phone usage is, up 48% this week. Anyone get that and get really depressed? Yeah. Right? You guys pretend you don't see it, you just swipe and you're You're using your thumbs all the time. It's kind of endemic to what we do nowadays. Why? Because we use it for so much. My 80-year-old dad and 78-year-old mother are getting proficient at using their thumbs on a cell phone. They still don't spell very well, but they're getting more proficient using their thumbs, right? So the idea being, the more we use something, the more those regions of the brain expand, get new connections, and ultimately increasing gray matter. So gray matter is the cell bodies, right? So we get growth in those brain regions. This is a really good example of that, if you could see it. So this is actually a study in primates these were actually squirrel monkeys. They learned to reach and grasp at blocks. All right, and basically all it's showing up here is the area of the brain, the region devoted to the hand for reaching and grasping. After training, that region is much larger. And then you could take the squirrel monkey, not have them involved in the experiment for a year, bring them back in and have them do the same task, and the region of the brain is still expanded. So what it's showing is that you could train this little squirrel monkey to grab a block, it retains that information. So how does that relate back to us? Think about riding the bike. You learn to ride the bike once. You retain that information for a long period of time. All right, so why do we care about this? Well, we need to understand the process of learning to understand how we can apply what I really like, shocking people's brains, to the learning process. Specifically, we use something called TDCS. You'll hear that term a lot when they get up and talk. TDCS is transcranial direct current stimulation. We put wet sponges and electrodes on your head. It's not electroshock therapy. We're not ridding you of schizophrenia or giving you schizophrenia, right, for that matter. No, we are applying very small currents to your brain in order to ultimately prime the brain, get it ready to learn. All right, these are some of the examples. The one you can't see up in the upper left, that's what we actually use for research. It's the one that looks the most like medieval and not hyper-tech. The bottom left here, that's actually being sold by video gaming companies. So some of you are the big active gamers, if you know Streepy, he's a big Fortnite player. There's probably guys he goes against that use this weird thing, right? So there's actually off-market devices for TDCS that people buy and apply to their own brains. 10 out of 10, do not recommend, right? Don't self-TDCS. And then, it's even gaining popularity. The problem with this is the research hasn't been done yet on it. People want to make a buck on it, like the video game companies, but there's not actually good research showing its efficacy, if it works. So that's where we step in. How does it work? Really simple concept. I have all these cells in the brain. They're sitting right here, this threshold. Think electrically. Some of you don't even know about what generates action potentials, all that. You don't have to know all that. Think the cell sitting right here. It needs to get up here to fire. All we're doing when we apply the brain stimulation, we're just moving it up slightly. So what does that make it? Easier to do what? Get to firing threshold. That's all it is. We're priming the cell. So the simple idea, kind of filling the cup. We're just getting her ready, right? So then when you go to do whatever the task is, when you go to learn, it becomes much easier to do. The cells are all ready to go. All right, so that gives you some of the idea behind how it works. Okay, realizing a lot of this you can't see very well anyway. This one you can kind of see. There's a big process that goes into how the cells learn and eventually adapt. All right, just know that over time, the more you use them, right, the better they function. Okay, that's all it is. Now, there's a lot of individual factors that go into it. Anyone that can tell you this is exactly how this happens is wrong, because we cannot make those measurements in humans yet. Why? I can't take brain tissue out of a living human yet. I don't know if you know this. I don't know if I could pass IRB with that. But you can do it to animals, so we have a basic idea of what's happening in animal brains post-mortem, but we cannot take a lot of these measurements out of humans. And what's the difference? Humans give feedback. Even if I train a primate to do something, to learn how to grasp a block, do anything like that, can they tell you what's going on? Can they sit down and have a conversation with you after the testing session? No. So we kind of have this limitation, right? I just want to say that up front. But these are some of the suspected changes that could be going on. So this brings us to the main point. Is TDCS the new PED for motor learning? There's other things that definitely can influence motor learning. All right? One being Adderall, stimulants, caffeine. There's drugs, but I also hope you would recognize, I think Adderall has some downsides to it. Right? It's not going to be something, I'm going to go throw darts with friends. I want to get better. Let me take my Adderall. Right? Not really its intended use. But is it a method that we could use, this brain stimulation, that you could sit down while you're gaming with your friends and get better while using it without any negative adaptations or maladaptations? There's a potential for that. And that's why we investigate it. So just to give you that idea. All right, at this point, I will pass off the non-functioning microphone and clicker and spotlight to Dad.
All right, guys, I know some of you already, but again, I'm Davin. I'll be presenting on a recent publication that we have based on TDCS in a motor learning task. To be exact, it was dart throwing with a non-dominant hand. Oh, I pressed the wrong button. There we go. All right, for this study, we recruited a total of 58 adults, approximately 23 years of age. We actually had 62 were excluded for massive standard deviations. You can't see these images super well, but essentially what this is illustrating is we tested 3 different types of TDCS. So Dr. Riley had mentioned that we're essentially trying to fill the cup to reach threshold. With TDCS, we can also kind of lower the quantity in the cup. We can empty the cup, if you will, with cathodal TDCS. And so we were interested in the effects of cathodal TDCS compared to anodal TDCS, which is the sort of facilitatory, and then also a sham TDCS to see if just having the TDCS device on was causing the effects. So I know he mentioned the TDCS device we use, but to be exact, we were using the Soterix brand TDCS. It is a 1x1 low intensity stimulator. It's actually run by 2 9-volt batteries. So again, kind of putting this in perspective, a 9-volt battery isn't an incredibly high voltage, right? It's not going to be able to cause a lot of harm or damage or anything like that. I can't stress enough just how low intensity these currents are. So we provide 1 milliamp of current for 20 minutes while subjects essentially practice a dart throwing task. The darts that we used and the board itself were all competition grade. We tried to standardize that because if you've ever used darts or played with darts, you'll find that there's a lot of variation, even just from dartboard to dartboard or from dart to dart. So the way we tried to control for some sort of consistency between subjects, we wanted to make sure that subjects were comfortable to use their own throwing technique, but we also wanted their throwing technique to be consistent throughout the duration of the test. So we started off by explaining the best ways to throw the darts. We also instructed the subjects on how to optimally aim, those sorts of things. They were allotted 3 practice throws or 3 familiarization throws before actually starting the task. During the course of the 20 minutes of the study and the practice, we ensured that they were trying to maintain that same form that they started with. As we noticed them starting to deviate, we would instruct them to return to their original form. So a single session essentially began with subject coming in, they would fill out the IRB, they'd go through a brief screening using an Edinburgh handedness questionnaire to determine their hand dominance. For the subjects that were denoted as ambidextrous, we had them throw with their least likely to throw arm, which for some of the subjects may have been kind of a challenge to decide on. So basically give them a ball and have them throw it back to us. Whichever arm they decided to throw with was their throwing arm. And again, as I mentioned, they were allotted 3 familiarization throws. So during the practice, there wasn't a set number of throws that they were given during the practice. It was 20 minutes of stimulation, and then they threw pretty much as many throws as they could in that time. The range of throws was around 3 to 5 throws per minute for all of our subjects. There were initial 15 throws beforehand. Let me jump back here actually. So they did 15 baseline dart throws. We were looking at kind of their distance from the center of the target. We found an average for the 15. We followed up afterwards with 15 more throws to look at the change in the average distance from the center, which leads us to this point here. We had something, or we calculated something called the gain score. And so basically the gain score is the distance moved towards the center. So if we looked at their original score as being, say, 10 centimeters from the center, the average of their first 15 throws, the gain score is, if we looked at their post score being maybe an average of 6 centimeters from the center, their gain score would then be the 4. That's the difference between those two. And so what you can see here, it's actually quite interesting. The sham condition, the lines kind of bled out through the picture there, but you can still see the dots. Essentially our sham and our cathodal condition, so again the cathodal being the one that sort of inhibits, the sham being the one that shouldn't do anything at all, they were pretty similar. So we didn't really see a statistically significant difference between sham and cathodal. What we did notice though was a pretty significant difference in the anodal condition, so again our facilitatory condition, which started after the second quartile of practice and then maintained afterwards through the end of the test. So that was pretty profound. There was a slight trend in the cathodal group towards reducing performance, but again, there was no statistical significance in that, so that could have just been chance. And again, just to kind of show our baseline changes from baseline. So the anodal group and the cathodal group, I believe is about a 24% performance increase in the anodal group, whereas the cathodal group only showed, I believe, about an 11% performance increase. Again, we expected some performance increase in all the subjects. We weren't trying to completely ablate their ability to perform a throwing task. But what we did notice was that there was a big difference in the anodal group and the amount that they improved. So again, yep, 24. So the cathodal is about 12%, the sham group is about 13%. So what we can kind of garner from the study, what we can take away from this is that anodal TDCS certainly seems to improve learning or expedite learning. Again, this is over the course of a single session. We didn't do any follow-up sessions. So within that single session, that fast phase of motor learning, anodal TDCS seems to have an impact. This is actually really pretty significant, this study, because a lot of the TDCS work that's been done so far has been in these sort of like clinical laboratory tests, things that are very, very constrained motor patterns. And if you think about something like throwing a dart is a pretty complex motor movement, all things considered, right? Compared to some of the other things that have been, finger tapping sequences or dexterity movements. This kind of gives us an idea, if we're taking TDCS and we're trying to apply it to a real world setting, this gives us an idea that it might actually be a viable technology. So future directions with this, you can think about things like activities of daily living. So if you're thinking in like the rehab settings, the rehab clinics, TDCS is used sometimes in physical therapy. But if we're trying to say that it's going to have some sort of consistent, reliable effect, we need to know that that has a consistent, reliable effect in tasks that people are actually doing. Sports or esports, as Dr. Riley kind of mentioned, this is where TDCS has kind of gotten its notoriety. There's been some growth in the esports industry, actually a pretty significant growth over the last 10 or 20 years. And just like with any sport, there's a drive to be competitive. And so TDCS is a useful tool, potentially, in those realms to try to help improve performance. It's also not banned by the World Anti-Doping Agency. So, I don't think that esports are governed by that, but I could be wrong. Another big thing, brain-machine interfaces. You guys might not be familiar with those, but it's essentially the ability to control a cursor on a screen or a prosthetic device by thought alone. I know some of the more popular devices on the market, or that are kind of making their way to the market, are the Neuralink, which is kind of being researched right now. And personally, I'm really interested in expanding this beyond a single arm and looking at bimanual tasks, because again, there's only so much that can be inferred from doing single arm movements. And when we start thinking about the complexity of moving both arms, things get a little bit more challenging, especially with the TDCS montages. And I believe that means you're up.
With my non-functioning microphone.
Yeah, so it's the top buttons there, so I push the bottom ones first. It's those two, yeah.
Cool, thanks. All right, great job, Devin. All right, so the next study that we're going to talk about that we recently got published this year, actually, is neuroenhancement of a dexterous task with anodal TDCS. So unlike darts, which is more of a gross motor movement, it is a complex movement. However, it's not a very dexterous task. It doesn't take a lot of dexterity in order to throw a dart. Maybe to hold the dart, but to throw it, it's kind of a gross movement. Versus something with tweezers is a little bit more dexterous. All right, so for this tweezer task, we wanted to specifically look at a dexterous motor task. So in order to do that, we took 40 subjects who had no previous history of neurological or musculoskeletal issues or diseases, and we randomized them to one of two groups. So one got anodal TDCS and one just got sham, so they didn't get anything. And they were required to use their non-dominant hand with the O'Connor tweezer task, which I'll explain here in a second, which you can't, again, see very well. So the top right image is the TDCS setup that Dr. Riley kind of already showed you guys what it looks like. However, sorry, I keep forgetting I have to be in the middle. However, on the bottom here, I'm going to try to outline it here if I can. So basically, it's just a rectangle, right? And you have pins that sit in a little divot, and then you have tweezers, and you have to place these pins that are about an inch long. They're just little silver pins, and you have to pick them up with the tweezer and put them in the hole. It's like a pegboard, essentially. And there's columns that you have to place them in. So each column is about 10 holes. So you place 10 pins and then move on to the next column. All right? So for what we did for our experiment, our experimental design, is basically we had everybody sit in a chair with the O'Connor tweezer task set in front of them, 90 degrees to their non-dominant hand, and we had them pick up with their non-dominant hand the tweezers. The only real instructions we told them was to make sure that their elbow stayed down, pointed down towards the ground at a 90-degree angle. Again, like Davin discussed with the dart task, you pretty much have your own type of throwing. We did give them a few parameters that they had to stay in just to keep it consistent between subjects. However, we did give them a little demonstration on like the best way to place the pin. Again, this is a dexterous task, so it not only is about how fast you can place the pins, but also the steadiness of your hand and the force you have to apply to hold the pin, because if you apply too much force, that little pin will just pop out of the tweezer, right? So it takes a little bit more control in order to perform this type of task. So once they got their setup, once they figured out, okay, this is how I'm gonna pick up the pin, place it in the peg hole, then they did a baseline pin placement of 50 pins, all right? And then we placed the electrode set up. Again, they're randomized to either getting anodal TDCS or no TDCS, sham TDCS. And then they did a full 20 minutes of just placing pins. So what we would have them do is place 10 pins or one column, and then they'd take a 30-second break. This was to allot for possible fatigue, because me personally, I had to try this out, and it was very fatiguing of your hands because, like I said, it takes a lot of control for those little hand muscles to be able to place those pins properly. And then they got a rest for 5 minutes. We took off the TDCS, and we had them do a post-50 pin placement. So overall, we looked at how long did it take them to place those 50 pins before and after the 20 minutes of simulation. And then we obviously took pre to post time to place those 50 pins. So we looked at the time before and the time after. And then in the 20 minutes of practice, time to place the first 5 columns of the 10 pins. So there were 10 columns. The first 5 was the first half, so roughly 10 minutes, and then the last 5 were the last half, roughly 10 minutes. So for our results sections, like I said, these are in halves of practice, so there was 20 minutes total. So the first 10 and the last 10. As you can see, the TDCS group and the sham group both placed about the similar amount of pins. And both groups performed better in the second half of the 20 minutes than the first half, just slightly. And then time to place pins, this is where it gets interesting. So on the pre, that's everybody, which you can't really see, but sham is the white circle that you can't really see there. But so you can see pre, they were pretty much very similar. Even in the practice, they were very similar in their times, but then you can see in the post, that 50 pin placement post, there was a significant difference between the anodal group and the sham group. So the anodal group actually got a lot faster than the sham group placing those 50 pins. And then you can see the overall percent change from the beginning, the pre-50 to the post-50, which again, you can see that the anodal group did significantly better than the sham group. So what does this mean? So we actually showed that we could increase or enhance reactivation. That's my study. We can enhance time, the speed in order to place the pins, so everybody got faster in the anodal group. It can also, results of simulation were obviously different, so we can obviously say, well, the only difference between these two groups was if they were getting stimulation or not. And this could be possibly due to neuroplastic changes, so plasticity in the brain. Essentially what Dr. Riley is talking about could be enhancing those motor pathways with TDCS. And again, this was only one session, so this is just the fast motor learning phase. And that's why Davin and I's research is looking more into the consolidation and the slow motor learning phase. Can we see if TDCS actually helps enhance over time rather than just within one practice trial? So this is all important because obviously, like Dr. Riley mentioned in the beginning, for people who are athletes, people who play musical instruments, or you're trying to learn how to play musical instruments or be better athlete, or even people for surgical training, specifically with the hand dexterity, they need to be able to manipulate their instruments fast and efficient. So there's a lot of potential that TDCS offers. So what we're doing currently, this is my current research that's going on. So reactivation-induced motor skill learning, enhancing motor skills with ATDCS for a choice response time task. So essentially, how do we learn a new motor skill, right? We talked about it. There's fast learning, slow learning, there's consolidation, retention, acquisition, right? So we acquire it, consolidate it, retain it. And kind of what Riley alluded to was practice makes perfect, right? We've heard that all of our lives. So does practice time make perfect, or does practice just itself make perfect? Do we have to practice for a long period of time to be very skilled at something, or do we just have to practice multiple times to be skilled at something? So what I want to know is, can I practice a new motor task for, say, 5 minutes and still get the same motor performance as I would if I practiced that task for 20 minutes? So what we're currently doing is we're measuring neurophysiological changes via TMS, so transcranial magnetic stimulation. I won't get into it too much, but essentially TMS is a super threshold, so it causes an action potential to occur at whatever muscle we are recording from. And it essentially helps us understand if there's physiological changes occurring while we do our interventions with TDCS. So we do it before on session 1, and then we do it on session 4 as well. And then in between those, we have a game. So it's called a choice reaction time task. You guys have probably seen this before, but essentially it's a computer task that you will play with your non-dominant hand. You'll use 4 fingers. And you will basically click the key that corresponds to the box that has the X in it as fast as possible, but also as accurately as possible. And then, depending on what experimental group you are assigned to, you will either get TDCS or you won't, or you'll play the game for 5 minutes, or you'll play it for 20 minutes. And I have 6 experimental groups total, but essentially what I'm looking at is, can we practice for a shorter duration and still get the same quality of performance? And then if we can we enhance that even more with TDCS? Because obviously from our previous research, we have shown that TDCS does cause behavioral enhancements, but can it cause behavioral enhancements and physiological enhancements as well? All right, next time. Is there a fake microphone?
So there are a lot of similarities between our research projects, so I won't belabor those points, but what I will highlight are the differences. So what we've seen so far is that TDCS does work in unimanual tasks, so one-sided tasks. There's been some investigation into bimanual TDCS tasks, but it's actually a pretty small body of literature, about 40 studies in the last 20 years, compared to more than 3,000 for unimanual tasks. And for me, that's very interesting. Again, we think about the kind of applications in a functional setting. So what we're looking at with my study is essentially, can we enhance learning in a sort of complex bimanual task that simulates something someone might actually do. And you can't see it super well, but what I'm using is a game called Super Tux Kart. It's essentially Mario Kart, but for licensing purposes, it's not Mario Kart. But we've modified the control scheme. We've modified the difficulty to make the task very, very challenging to master, but relatively easy to learn. And so we're looking at, over the course of a few sessions, how does someone improve, how do they plateau, and do they continue to improve from session to session? Also, do they retain the things that they've gained from session to session? And we're actually using this sort of bimanual TDCS setup, or this bilateral TDCS setup, compared to a lot of the unilateral setups where they just stimulate one side of the cortex. So again, my interest or my goal is to kind of see how this works over multiple sessions and also see how this specific stimulation montage works. So yeah, otherwise we do the TMS stuff, measure, neurophysiological measures of excitability and all that boring stuff too. So, cool. Do you guys have any questions for any of us? Come on up. Any questions for Michaela if you don't have questions for me?